I was trying to get some worksheets printed out, but the internet was down this morning. I don't know if you guys knew that or not. So I got some stuff printed off. It must have gone out like mid me trying to print stuff off. So the worksheets are on Canvas or the files section. You're going to want to probably pull them up at some point because we're going to talk about it a little bit today, how to do them. I don't have them printed off, so you obviously can't start on them, but we can at least walk through some of it. So first, I just want to talk kind of casually about the three things that I handed you, all right? One of them might look a little familiar. Did I start recording this? Yeah. Okay. So we're moving into, it's called molecular orbital theory. Okay, that's what MO theory stands for. This is going to be probably a little confusing at first. We're going to spend some time on it, right? A lot of practice. It's going to seem really weird. But usually, most classes and most books are going to structure to where you don't get into this stuff until later. But it explains how electrons really work. There are two models. The model that they use to introduce electrons to you and how they work, is that they exist in this shell around, they just kind of exist outside of the nucleus, isn't 100% true. Whereas MO theory is what's really taken as the truth. Alright, how they really work. So before we get into the nitty gritty on going off and talking about structures and compounds and things like that, I want to make sure we understand how electrons work. So, let's see if I can, this thing wants to work today or not. If not, it's not a big deal. So, you've got three handouts, alright? The first one that you have is a little grainy, but you should be able to understand it all. Looks like this, right? This one. Okay. What those are explaining are these shapes. These shapes are going to explain what those are. So you have this, they're non-colored. Alright, this is just a reminder. You're not going to be made to memorize all the different shapes of the molecular orbitals. Alright, but in essence, what you're looking at here, if we're going to look at this in tangent, and I wish this was working so I could go back and forth. There we go. Okay. So, all of these, right? Don't worry about the number next to them. These are all the S shells, right? So, you see, the one exception is us over here with helium. And I use this to kind of explain why helium is an odd case that's satisfied at 2 electrons when any other element's not satisfied, right? We talked about that very briefly. I explained how that was MO theory. These are your S orbitals, right? And so what you're looking at, shape-wise, is simply how you would expect the electron cloud, where electrons normally reside in, right, is a sphere. Okay, just this nice ball where the electrons reside in around the nucleus. Right, not too complicated. As we move along, as we're reading left to right, right, that's how you read this. You go left to right and go down just like you would have looked. You come across your first P shell. This is where you get, like, you see carbon, nitrogen, oxygen, fluorine, all those live. You come into our P shells, which are what look like this. Right, they're dumbbells. Then this is the only time we're really going to touch on the transition metals a whole lot. As we keep reading, our number before the type of orbital increases, we come across our first D shell, which now we start to get some real funny shapes, right? Especially that guy right there. But you start to get things that look more like a flower. These are three-dimensional. We understand how to look at these, make sense of these or no? You have the X, Y, and Z axis, because we're talking in 3 dimensions here, right? And then lastly, you've got your F's all the way down here. We're never going to touch these. But just know they get really weird. So what's the point in doing any of this stuff? Alright, so if I were to ask you, we're gonna work on filling out shells. That's what the homework is. If you guys could actually get on your iPads and go to Canvas, go to Files, should be under Homework. You should see Electron Configuration Homework 1 and Electron Configuration Homework 2. We're going to talk about how we make sense of these. So all of these are energy levels, right? That's what all of these are. As the number before the letter, right, so 1s, 2s, 3s, as that number gets larger, the energy capacity of those orbitals gets higher. Right? The same as with the P's, the same as with the P's. We're going to talk about that more in just a second. Okay? We're going to explain how this applies to the work that we're going to be doing. And then the last thing I want to just introduce to you real quick. You guys find what I was talking about? Files, it should be under Files, Homework, should say Electron Config. Okay, 1 and 2, there should be 2 of them there. Okay, good. You guys remember when I mentioned electronegativity at all? Do we recall that? Talking about the greediness of an element. So this is the third handout. You guys are going to be more than welcome to consult these things on quizzes, right? So take good care of these handouts. The value, yours are grade, right, not color. So look at the value. Fluorine is going to be the highest here. If you recall, I told you all that fluorine is the most greedy element of them all. It's going to hog all the electrons when it forms a bond. The value for fluorine under electronegativity is what? Can you read it, or is it too dark? The value for the electronegativity of fluorine is what? Can you read it? What is it? Okay. It's the highest number you're going to find. The lowest that you're going to find, I don't even know what this is off the top of my head, francium. Yeah, I was right. Okay. So this is the lowest. So you notice a trend, right? As we move diagonally up and to the right, the electronegativity increases. The ability for the atom of that element to hold on to electrons increases. This is going to matter more when we get into some more detail. This is just introducing the concept. And the question is, why? Why does this happen the way that it does? So if we look at fluorine's group, right, what happens to the overall electronegativity as we go down the group, which is the column? What happens? Goes down. Okay. It's still higher than the stuff all the way in the bottom left, right? We'd agree with that too. But what is happening? Fluorine, right? If I were to picture my nucleus, what resides in the nucleus? You've got 3 particles: electrons, protons, and neutrons. What reside in the nucleus? Protons and neutrons, right? Are there more protons and neutrons at fluorine? Or if we go down to like iodine? Which one has more protons and neutrons? Fluorine or iodine? Iodine, right? Because our atomic number, our atomic mass increases as we go down the periodic table. So this is just kind of arbitrary. But if we pretended our nucleus for fluorine existed something like the size of that, alright? Iodine would probably look something more like that. It's larger. There's more stuff. So it has to be bigger. And then you go back to all of these different shapes, alright? I told you as we read left to right, we're increasing, we're adding to it. So fluorine's right there. So we read left to right. It has 1s. So that orbital exists. Then it has 2s. That orbital exists. And then what's next? 2p. Okay? And that's where fluorine cuts off. We just read left to right. Now if we wanted to go all the way to iodine, which is right here, right? I would have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. We understand how I'm reading that off, right? We understand I'm just going left to right and down, just like you would a book, right? So that iodine has a lot more stuff. So all those pictures that I showed you, every time I say 1s, 2s, I'm adding a sphere, right? So 1s is one sphere, 2s is a separate sphere. So there's more junk out here too in iodine than there is in fluorine. There's a lot less junk, okay, because I didn't have to go nearly as far. So what electronegativity is referring to is how well we stated that neutrons exist in here, which are neutral, and protons exist in here, which they carry what charge? Good. So if I have a bunch of positive charges floating around here, and our electrons have what charge? Okay. Say I introduce an electron to both of these, right? This is fluorine, this is iodine. If I were to introduce an electron to both of these, do you think the positive charge on fluorine or iodine would have an easier day at holding on to the negative charge of the electron? Which one, which nucleus would have a much easier job at holding on to that electron? Fluorine, yes, I agree. Why? There's just less stuff, right? Because I sat there and rambled off all those different electron shells. So you've got all these different electron shells floating out here in iodine compared to fluorine. Plus, you've got neutrons that are, a bunch more neutrons that are floating around in there too, right? Which are all getting in the way. So overall, it would make sense that iodine has more fluff, what is it called, fluff? Stuff getting in the way of holding on to that electron, right? So it's not going to be able to hold it as strongly as fluorine would, because there's just less stuff in the way. Which then should agree with our electronegativity chart. What I just said was that iodine should have less of a hold than fluorine on an electron. What's the value for fluorine? It's 3.98, right? Iodine, what is it? Is that less or more? Okay, so our electronegativity chart agrees. So in essence, there's some complicated math, some complicated science, right, that go into calculating these numbers. But the reason you see the trend and the pattern in these numbers, overall when we're talking electronegativity, is in essence because of the fluff that they have. So I should see an overall trend where my electronegativity, as I go down then, As I get more fluff, as I go down, what should happen to my numbers? Huh? Yes, they decrease. Right. Because I'm adding more stuff in the way. This is just think of electronegativity as a value that tells you how good it is at holding on to an electron. That's all you have to think of it as. So then as I move from left to right, I expect it to do what? As I go from the left to the right, I see it do what? It increases. How good it is at holding an electron, right? That's what the value is. Why would lithium not be as good as holding onto an electron as fluorine? Ignore the value. Think about what we've learned so far, right? Ignore the value, the electronegativity number. Why would we expect fluorine to be a lot better at holding onto an electron than lithium? I know this is asking you to think before break, but
That doesn't make sense, but shouldn't it have some trouble?
why would it be greedier at holding? Why is it able to hold on to an electron more than lithium? What's our valence electron count for fluorine? Okay. What is it for lithium? Okay. And there are two magic numbers to satisfy our valence electrons. Are what two numbers? And an 8. So this is really, really close to being a complete shell, right? At 8. It has to gain one more electron to be really happy. So once it gains that electron, it doesn't want to give it up. Lithium doesn't give too much of a crap about its electron, because it'd rather lose it. It's easier to lose it and satisfy the shell by sitting at 0 than it is to try to work its way all the way up. So that's why, as you go from left to right, as you get closer to being more complete at 8, you see the electronegativity increase. Right? So it goes down as you go down, and it goes up as you move right. Those two trends make it to where if you move diagonally, your electronegativity increases. Okay? Oh, this is probably confusing. It's going to get a whole lot more confusing here in just a little bit. Alright, well, we're going to spend some time on this, and it will make sense of something. This is tougher stuff. This is weirder stuff. This is going to probably be stuff that you've never even heard of before. So, how much time do I have? 15 minutes. So let me ask a question real quick. Make sure we at the very least understand this. If I'm looking at copper, which is Cu, alright? Does copper have a higher or lower affinity for an electron than iron? They're both in the middle. Cu should be copper, and iron should be Fe. Which one has a higher affinity for an electron? Copper or iron? Why?
Because it's
Just very simple.
closer to having
It's what? We haven't talked about how many valence electrons exist in transition metals. Just speaking strictly on electronegativity, not value. Right. And it has a higher number. Does copper exist at what? What's the electronegativity number of copper? 1.9? And then what's iron? So that is what? copper has a higher electronegativity value than iron. Just take that away from the chart. We'll talk more about the trends, but just take that away for now. The higher the number, the more likely it is to hang on to an electron. So looking at your assignment, that's not really an assignment, but it's going to be at some point, right? A little bit of time. Let me pull this up too. What do we do with these shells? That's what we're going to talk about next. So if I'm looking at homework 1, alright, I'm going to show you all how to do this. Homework 1 asks, number 1, it says write the long form electron configuration with the following elements. We get lithium. So the first step we do is identify where lithium is on the periodic table. We find lithium.
No.
You can look at the electron configuration table because you're going to be needing that. That's the thing with the 1s, 2s, 3s, all of that. Kai, do you not have one?
What?
Do you have one?
This?
Yeah, it's there. Where's lithium? We found it.
Yeah.
It's on the left side. Li.
Top
Right there. We read from left to right. So what do I start with?
What is?
1s. Okay. Now, when we're writing these, we're talking about the total number of electrons in it. We've learned how to find valence electrons, right? We've got that trick down. That's an easy one. What we're doing when we're talking about this is how many electrons total exist in this element. All right? So 1s, we're going from left to right.
What is?
There's 2 of them. So what we do, you see 1s on hydrogen and then 1s on helium. We see that? So you write it like this. 1s with the superscript in the top right corner, 2. Right? Because we've had to go completely through 1s to get there. Now, next up is 2s, right where we bump into lithium, right? So we then go 2s. Now let me ask a question. If there were 2 1s's, right? You had hydrogen and helium. That's always going to be a rule. So there's 2 total slots in the S shell. Do I come across it first or second? First. So what would I expect my number to be then? 1 or 2? If I come across it first,
One.
yeah. And that would be the long form configuration for lithium. Alright. Anyone lost so far? Show of hands if you're lost. It's okay if you are. Okay. Magnesium. This is the next one. I don't have much time.
Is it Mg?
Yeah. Right here. Yes? Okay. So I start left to right. I work my way down the periodic table till I get there. My S's are full, so I've got one S. One S2. So this was lithium. This is magnesium. I then go to two S's. Alright, those are full. I move on from those. 2S2. I then have to cross over, as I'm reading, to my P's. How many P's exist?
6.
Good. Okay. So a full P shell would mean it would be 2P6. Alright? I then move on to three S's where magnesium resides. Is it first or second?
6.
Okay. So I would consequentially put a superscript of 1 or 2. So that's the long form for magnesium. What's it ask for next? Potassium. Let's do oxygen. We see where oxygen is at, right? Is my 1S full?
Yes.
Okay. Is my 2S full?
Yes.
Okay. Now, is my 2P full?
No, it goes to 4.
Goes to what?
4.
Good. Do we all understand how we're getting there? Right, because we just simply count 1, 2, 3, 4. Right. It seems really complicated. It's not. And there's a little cheaty shortcut too, because scientists ultimately are lazy. Let's say I wanted to go to selenium, which is right here. If I wrote the long form every time for selenium, I would have to write 1S2, 2S2, 2P6, 3S2, 3P6, 4S2. B has how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so when you come across D, the max is 10. 3D10. And then finally 1, 2, 3, 4P4. I want to write all that. So what you can do, the shorthand version, which is what that second section asked about, right? The abbreviated electron configuration. You take your noble gases, the most recent noble gas. Which noble gases reside on what column? Do we remember talking about that? We mentioned it. Do we remember though? It's the last column, right? They're stuck up, they're noble, they don't do much, right? Noble gases is the last column. So the most previous one, noble gas, to selenium is what? If I were to go back, as if I was reading, from left to right, top to bottom, would be AR? Yeah, which is argon, okay? So the way I shorthand this is I put argon in brackets, alright? And that basically covers 3P and back, is what that does. That lists it all as 3P and back. So then I just have to move on from 3P. So I start here. So I start at 4S. 4S2, because it's full. Then I go to 3D. Right? And then, if I'm going to selenium, what would my last one be? Be 4P what?
4.
Good. Okay. So that's shorthand. It's using the previous noble gas. You put that in brackets. That's all I have time for today. I know I probably sprinted through that, maybe a bit confused. There is no assignment. You are more than welcome if you want to look ahead for some weird reason. Go ahead. But I'll be printing those off, the 2 worksheets that I have posted on Canvas, and we'll be working on those in class. Alright. We're gonna get tons of practice on this. It'll make sense. It'll make more sense. Alright.